This is the 8th installment of Advanced J1939. So in this installment, we're going to take a look at the data. So we're looking more at data that is actually being transmitted and received by the controllers that are on the CAN bus. So before I can talk about that, I probably have to show the obligatory OSI, Open Systems Interconnection model. This is a 7-layer model. Sorry, this is some really boring stuff, but I do want you to have this reference that you can go out and take a look at this. So I'm using the foremost authority of pretty much everything, right? Wikipedia. So if I look at this 7-layer model, what this is it's basically it's a fundamental of computer science. It's a fundamental of how controllers communicate on some sort of a network. So it isn't just applicable to CAN or J1939. So pretty much everything that we've been talking about so far is this physical layer. These are the controllers. This is the twisted pair, the yellow and green wire, the inductance and the capacitance of that, the terminating resistors, the controllers, the hardware, the CAN transceivers. These things are pretty much all part of this physical layer. So we're moving into the actual data itself. We're getting into these other layers. Some of these are applicable to J1939 and CAN, some not so much so at all. But I do want you to make aware of this, because if you start doing your own research on this, you're going to see these terms. So the physical layer, the data link layer, network, transport, session, presentation, and application. So we're going to move into this kind of the kind of a combination of the data link layer and the application layer, I guess is the best way to put it. I'll stay out of the computer science piece of this, mainly because I'm definitely not an expert in it, and this stuff was really boring to me when I took it in college a long time ago, so I'm not going to bore you with that. All right, taking a look at the information that I see on the oscilloscope. So I've got a real network here that I'm analyzing. I've got a couple of controllers that are on this network. And as we've talked about before, we can see that the bus is sitting idle. So CAN works because one of the things that the way that it works is, as long as the bus is sitting idle, anybody can go out and communicate a message. So this is a 500K CAN bus. We can verify that by the bit length here and take a look at it. But we can see that it's pretty well utilized. I mean, it's and I can kind of eyeball this on the scope and say it's probably used about, if I look at the blank spaces that there are between controllers and all these messages and these packets of messages, I don't know, maybe what, 30 or 40% that it's utilized, probably close to 40%. We could get an analysis tool to take a look at it and see, but it's there's plenty of room, there's plenty of time where the bus is sitting idle, where if a controller has a message to transmit, it should be able to get that message out. Granted, there are going to be instances, as we talk about with arbitration, and we'll look at some of that, where the controllers, because there's more data here than there's more than one controller on the bus, multiple controllers could say, I got a message that I want to put out, and they would put that message out at the same time. So the bus has to be sitting idle. There's a period of time that the bus has to be sitting idle first. In this case, it's several microseconds that the bus has to be sitting idle, and you can see here my time base is milliseconds. So 58.6 milliseconds to 58.8 milliseconds, for example, they're pretty much around there. For sure, the bus is sitting idle, right? We can see that it's that nothing is transmitting, and so when a device, any device, has a message that it has queued to put out onto the bus, it's like, oh, I found a fault, for example. I set a DTC and I need to put that information on the CAN bus, or something changed and I need to inform, the other controllers of this. The transmission's getting ready to make a shift. I need to let everybody know that I'm going to be making a shift. The engine, its current speed and torque. It's like, oh, everybody needs to know this. The transmission might need to know it. It's like, here's my current speed and torque. So we'll talk about some of these messages. Some of them are broadcasts that are on a periodic, so it's every as low as every 10 milliseconds, perhaps. There's a message going out that it has to. I send this message out. That'll be for another episode. We'll talk about broadcast messages versus request messages. So I don't want to get bogged down in that, but we'll take a look here. The data link sitting idle. This is the recessive state. It's not considered. You can see here by Pico, they've said this is not a logic 1. even though it's at the logic level of a logic 1, there's no message in progress. So it's really just the bus sitting idle. The difference in voltage in violet here, purple, is showing that it's approximately 0 volts, right? It's CAN high minus CAN low. This is a real network, so there's some actual noise out there, okay, that we can live with. We know that's there because of the capacitance, the inductance, and even some electromagnetic interference from outside of my system. So that's the reason for this, for the lines not being straight, horizontal, vertical, as we've talked about in other episodes. So if I look at this, the first thing that any controller has to do if it's going to use the data link, if it's going to use the CAN bus, if I'm going to use that, I have to put a bit out there. And since it's sitting in recessive state, there's only one or two other states, and that's the dominant state. So to say I'm going to use the CAN bus, and to do that, we put a bit out. So we put the start of frame bit out, and we'll take a look here. We'll kind of verify. Whoops. Okay. Yep, there we go. Get my rulers here. Sorry, I'm just learning how to use this. If I take a look at my difference in time, my delta t up here, my delta time, that's 2 microseconds. So 2 microseconds. Okay, we'll go ahead and do this. 2 microseconds, if I put this into a standard calculator, so that would be 0.000002. And if I want to see what that is in baud, I do the reciprocal of it, 1 over x. If you remember this from algebra or any of that other math that you probably were bored with in school, we can see that's 500,000, which is 500K. So it's the reciprocal key is your friend on the calculator anytime you're doing anything with CAN or with anything with time on oscilloscopes, etc. This is the reciprocal key. So 2 microseconds is 500K. So there's 1 bit. So we got the first bit, and since it appears that nobody else is going to use the CAN bus, so nobody else is also trying to do this at the exact same instant in time, right? You check. All the controllers now see this, and they know that somebody's going to broadcast a message. So if they've got a message to broadcast that's going to come 2 microseconds later, they got to wait because somebody's already started transmitting. And so we can see the first thing that we're going to transmit is this thing called the priority. And I've got this set in binary right now. I'll change it over to another form of numerical, of a number-based system that's more commonly used. So binary is base 2. There's only 2 possible states, 0 and 1, and then you start counting over again. And you can look at that in a Windows calculator or whatever and play with that and see how that works. We'll do that here in a minute. But looking at this, we can see that somebody started using the bus. This is a low priority message, and I know that because the first thing it's putting out on the CAN bus is a logic 1. That indicates that its priority is not that important. So this is not that important of a message. And we know from the rules of arbitration, because he drove this to a logic 1, if a very important message would have started at the same time because of arbitration, if both of these would have driven the starter frame, they would have driven the CAN bus to the dominant state. If there is a more important message, the priority bit, the first one, is probably going to be a logic 0. And so we would have seen this still be held after the starter frame bit. It would have been held at the dominant state. That means if this controller, whatever it is, was trying to send this message with this lower priority, so a higher number, it would have had to stop transmitting. It would have lost arbitration. So this is typically where arbitration, where the controllers detect this. This is called the arbitration field, and it is this priority. So priority being the first things that we send. If you pull up the J1939 specification somewhere, if somebody gets that for you, and you look through it, you're going to see that there is a lot more information here than I'm going to give you, than what I'm going to give you. And it's because it isn't so important for understanding the basic concept of this. And if you're going to be an engineer, yeah, you've got to know that stuff. If you're going to just look at stuff in the field and understand how this works and look at scope patterns and data like this, it's not so important. Maybe one of these days you'll find a unique example where it's like, oh, I needed to know that. It's highly unlikely. So I'm going to keep this simple. I'm going to keep it simplified. So any sharpshooters that are out there that want to criticize this, have at it. I don't care. If you could do a better job, please do it. Send me a link to it, and I'll learn something. So thank you. But I'm just what's important is that we see that this has a priority which is low. I'm going to look at another message. We'll find some other message that's out here, and we'll take a look at the priority of that message, and we'll see if it's a higher priority. Well, no, that one's still the same. What about this one? Let's take a look at another one here. And it looks like here we have a message which is a higher priority. And the reason I can tell that is, as I said, we have the start of frame bit, and then we have the first bit of the priority. And if I look at this, it is a logic 0. That means if somebody else that had that other message which had a lower priority wanted to transmit it, it would have lost arbitration, and it would have had to hold its message, and it would have to send it later. And so oftentimes you'll see these in packets like that. You'll have a message, there'll be a little gap. Let's see if we can find one here. And you can see right here. So here's a bunch of messages. And as soon as we can see pretty much as soon as that bus is let go, this end of frame, we got a message that came through. So there's a good chance that this controller that's sending this message, the start of it, just because of this end, we've completed it. There's been a time period after the message. The bus has been sitting idle long enough, and it's like, okay, now I can send my message. And there's a chance that it wanted to send this message back here at this time. Same thing with this one. We can see the same things occurred. It's like, here's the end of frame. The bus is sitting idle for long enough, a few microseconds, and it's like, oh, now I get to talk. And so this message goes out. So this is arbitration. Otherwise, these messages would be stepping all over each other. And you can't have that, because I can't have this message come on top of this one and start in the middle of it, because someplace where it's driving to a logic 1, this message will invariably drive it to a logic 0 and will corrupt the message, and the message will be junk, and we'll have to start it over again and send it again. So we'll talk about a lot of those concepts as we go along. This is more just an introduction to showing you real data on the CAN bus and how arbitration makes this possible. This serial link, I've got 2 wires that are time sharing that wire, and they can't both be at the timeshare at the same time, right? It's like double booking a timeshare somewhere in Florida or wherever, right? You've got to wait till the other people are out of the timeshare before somebody else can come into the timeshare. So if we look at it in that regard, this is time sharing the pair of wires, and the way we're able to do that is because of arbitration.